Right. Okay. Good morning, guys. So today we are going to continue our discussion of structural properties of materials. So this has to do with. So yesterday, basically, we seen equilibrium. 2 days ago, we seen equilibrium structures. So yesterday, perturbations of equilibriums, that equilibrium, that means deformations like elasticity. So this elasticity is about very long scale deformations. Okay, they happen on many unit cells, okay, on an entire solid. But you can imagine deformations which happen on a very much smaller length scale, which is the scale of bond lengths. So that basically is the realm of vibrations in solids or nanostructures or molecules. Okay. And what we want to discuss is how to calculate vibrational properties in molecules and solids. And I write phonons, thinking about solids, but it could be vibrons for molecules and so on. So let me stress that what we're going to see is in principle has nothing to do with DFT. It's essentially a brush up on what you have in the book by Ashcroft and Mermin. So in principle, all these things that I'm going to say, you already know them. We're just going to look at them from a slightly different perspective, which is focused on how to do calculations. Okay. So let's start with an example. So first of all, how we define vibrations? Well, we need to think about the dynamics of nuclei or ions. And yesterday we introduced a Newton's equation for the atoms. And that was coming from the fact that we first did the Born-Oppenheimer approximation, separating nuclear and electronic degrees of freedom. And then we made an approximation that nuclei can be described as classical particles. So at that point, we end up with a Newton equation. And the only bit that comes from DFT is the total potential energy surface. Okay, so the structure of the equation doesn't change. What depends on the calculation is this potential energy. So what we want to do now is to try and to understand how the notion of vibrations and phonons emerge from this. Okay, so the bottom line is that near equilibrium, this function is concave, and therefore you can imagine that particles will fluctuate around the minimum. So that's the origin of vibrations. So to understand that a bit better, we consider the simplest example as usual. In the tutorials we did the chlorine molecule. By yesterday in the lecture I described the nitrogen molecule. So let's stick to nitrogen. So this is a diatomic molecule. The only degree of freedom is the distance between the two atoms. And if you think about it from the point of view of atomic coordinates, so there are two atoms which live in a three-dimensional space, so there are actually 6 coordinates. Okay, so the Newton's equations, there will be 6 components here. But I'm telling you that there's only 1 degree of freedom. So the reason is that I would like to sit on a reference frame, in a reference frame where basically this molecule is not rotating and is not translating as a whole. Okay, so since for the translation and rotations we have basically 5 degrees of freedom in total, there is only 1 left, which is the vibration. Okay, so the only thing that this can do in our reference frame is to elongate or compress. So if you write down the equation of motion of this atom and this atom in this so along this direction, you find something absolutely trivial, which is the mass of the nitrogen atom, second derivative of the position with respect to time, is minus du in dx, which is the force. Okay, so the same story for the second atom. So that's the same thing written above, but for each of them. And then now, if you take the difference, okay, the distance x1, let's say x2 minus x1, that's the distance. So you have the mass of nitrogen times the second derivative of the distance with respect to time. So in this case, second derivative I indicate as a double dot. And that is equal to the difference between these 2 bits. So now this takes a few seconds, so I will not do it, but you have the detail here, how to get there. But the bottom line is that when you take the difference between those 2, you find minus 2 times the derivative of the potential energy surface with respect to the distance. Okay? So this is just a little trick to rewrite a problem where you're looking at equation of motion of one atom and the other atom into a problem where you only look at the time evolution of the distance, okay? Distance here, distance there. So at this point, the advantage is that we already calculated the potential energy surface for this molecule. So we did it for chlorine in the tutorial. I did it for nitrogen yesterday. So we can use this potential energy surface, basically, to calculate these derivatives and study the time evolution, okay? So this is the potential energy surface, is the black line here, okay? So if you remember chlorine, the shape is almost identical. The numbers will be a bit different, but the shape is identical, okay? So it's this thing with the potential web. So now this whole picture is to just make a point about energy scales. So this potential energy surface has a deep, I don't know, maybe 10 electron moles, below 0. And then the energy scale on the plot is about 30 electron moles, okay? Now the point is that if you are, suppose, at room temperature, by the equipartition theorem, 1 degree of freedom gets kT in terms of energy, okay? So room temperature kT is about 25 millivolt. So that means that the energies which are accessible to this molecule beyond equilibrium are in this range, basically, which is an energy of kT, okay? So this is a zoom of this plot. So we are really looking here, okay? So this is all the accessible energies which the molecule can take. And as you can see, it's a very, very, very small energy range. Therefore, everything we know about the shape of this thing is not really needed. We only need to know what happens very near the bottom. For this reason, what people do is, since this is a minimum, well, they say instead of taking the black line, okay, which is the complete potential energy surface, I can take the blue line, which is a parabolic approximation. So I replace the black line with a parabola, okay? So now just to compare, so the black line and the blue line on this side are the same as here, but here we are very near the bottom. So the parabolic approximation and the complete energy surface are identical, basically. Here clearly you see that the parabolic approximation starts deviating a lot from the potential energy surface. But in practice we don't care, because we never reach these points. So this is what we care about. So when you replace the potential energy surface by a parabola, that is called the harmonic approximation. Okay, that's all of it. So in practice, for calculation, what we do is to really, I don't know, go to MATLAB or GNU plot and say, oh, I would like to fit a parabola in this range to this object. So I will have my potential energy surface is equal to some constant, which gives me the baseline, plus coefficient times variable to the power of 2. So there is no linear term because it's a minimum, okay? So the first derivative is 0. So that's a way of proceeding, and these two numbers come from a fit. So there is nothing really. So we do first our DFT calculation, then we do a fit, and we obtain that. So if you use that, what is needed here is a derivative with respect to the distance. So this drops, and here you have 2 times 1/2, it drops. So it's k times the distance. So that's basically the term which goes on the right-hand side. And what we obtain is basically the standard equation for the harmonic oscillator. Okay? So there is nothing really, it's something completely trivial, okay? We agree with that. So what I did here is just to bring the mass from here to this side. So now this equation admits a solution that we teach in first year undergrads, which is basically combination of cosine and sine functions. So if you replace something like cosine omega t, you will find that this oscillates with a frequency which is given by the square root of that. Okay, I mean, I'm sure you are familiar with that. So basically, the frequency of vibration will be square root of twice this coefficient that we fit divided by the mass. Okay, so there is nothing really dramatic here. Now I want to give you a couple of numbers to see how it goes. So this constant again is the parabolic. So it is the second. Is the coefficient of the quadratic term in the field. And that can be obtained after calculating the potential energy surface. So you could do it on the chlorine atom. So after, if you look at your data. So if you take this coefficient, multiply by 2, divided by the mass of nitrogen, take the square root, you get a frequency, which is basically a 1 over time. If you multiply by h bar to obtain an energy, you obtain this value. So in the case of nitrogen, it's 288.9 millivolts, and the experiment is 300.4 millivolts. Okay, so that's about 4% deviation. So you see, things are pretty good at the level of a single molecule. So to do this, we don't need anything beyond what we already have from the tutorials, yesterday's tutorials, basically. So we just need to perform a fit. Now, I would like just to give you an idea of what happens if instead of using the parabolic approximation, you actually use the complete expression, so the original function. So you don't do the harmonic approximation. So if you avoid the harmonic approximation, instead of 288.9, you get a 304.2. So the frequency goes up about by 5 millivolts. So this is so the difference between this number and this number is what people call the anharmonic effects on vibrational frequencies. Okay, so these are quite small. That's why one neglects them in a first approach to the problem of vibrations. So that's not too complicated, but that's a molecule, is a diatomic molecule. So what we want to look at now is a more complicated situation where we have either a crystal, okay, or a polyatomic molecule. So a system with many atoms. So what we're going to see here is something where there is a bit of algebra, so linear algebra. And the only complication with respect to the previous case is that there are several atoms, several Cartesian directions, so it gets more messy. But the concept is identical, okay? So there is nothing different from what I just said. It is just slightly more complicated because there are more objects to take care of. So the observation in the case of, let's say solids is that if you are far from the melting point, the atoms vibrate near equilibrium. Therefore, you can write down, you can identify basically the average, so the equilibrium positions, and you can write down the time evolution of the position as the equilibrium position plus a time-dependent displacement. Okay? At that point, you can write down an equation of motion, not for the position, but for the displacement, right? So you have this equation of motion. So now we want to do something called the harmonic approximation, also in the case of solids. And the idea is the same as for the molecule. In that case, we had only 1 degree of freedom, so you perform an expansion in the distance, okay, around equilibrium. So in this case, there are many variables. So one has to just perform a Taylor expansion in on several variables. So what you see there is the baseline, so the bottom plus displacement times derivative with respect to displacements, and that's has to happen for every single atom, every single direction. Then you have the second derivatives multiplied by the square displacements. So this is identical to what I just said for nitrogen. The only difference is that we may have 10 atoms, and therefore we need to do derivatives with respect to 10 atoms times 3 Cartesian directions. So you will have 30 terms here. You will have 30 by 30 terms here, and so on. Okay? So the situation just gets more complicated, but the story is the same. So how does one enforce the harmonic approximation? So harmonic approximation means we want to fit something which is a quadratic function of displacements. So we neglect anything which is beyond order 2. And then the good news is that if you are at equilibrium, the forces are 0. But the force is minus the derivative of the potential energy surface with respect to the positions. So this has to be 0. So in practice, the harmonic approximation consists in killing this term, the other term there, and remaining with these two objects. Okay? So these second derivatives, they are the counterpart of the kind of coefficient that we could have fitted in the case of nitrogen. So in that case, we had one number. In this case, is a matrix of numbers. So this index is the atomic index. This is the Cartesian direction. Another atom index in the Cartesian direction. So before we had one atom, one Cartesian direction. Therefore, we had basically just one scalar number there. There is no matrix. Okay, so that's basically everything. There is nothing really that adds here. So what follows at this point is simply a way of trying to find a formal solution of this equation using this expression for the potential energy surface. So there is no new physics. It is just putting together maths in a way which is convenient. Okay? So we could skip all of it, but I would like to show you so that it's maybe more clear when people talk about phonon eigenmodes or phonon frequencies or things like that. You see what this is about. So the idea, first of all, is that I need the derivative of that with respect to the atomic displacement. So this is not there anymore. This is not there anymore. This is a constant, so it goes away. So this derivative basically drops one of these guys. So I'm left with k times 1 of the displacement. So if I try to write that, I have the mass acceleration on the left-hand side, and then k times displacement on the right. So that's basically my equation of motion. And these are, again, simply second derivatives of the total energy with respect to atomic displacements. So nothing really complicated. Now, what we can do is to define vibrational frequencies is to try for solutions where the displacement, okay, oscillates in time, using like a trigonometric function, okay, cosine or sine. That's the usual ansatz. So if you replace this inside here, second derivative gets out, takes out a I omega, so it becomes omega square, and then there is a minus, okay? The minus comes from I square, kills this minus here. And then what I did is just to bring this on the left and this on the right. So this expression, after inserting that, gives this thing. So that's pretty much all of it, okay? So we are almost done. Now there is one little extra step. So you see that, so you recognize that this is almost an eigenvalue problem. So because you have something like a matrix like that, I alpha j beta times an object which depends on j beta equal mass I omega square this object I alpha. So it's like almost an eigenvalue problem, okay? So it is not really an eigenvalue problem because here there is a mass which depends on the index entering here. So it's a bit messed up, okay? So people don't like that because it's difficult to solve. So what they do is to try to make a transformation to get an eigenvalue problem. The operation is quite simple. So instead of having this mass, so they say, okay, I'm going to use square root of mass, which is the same. I bring this on the other side, okay? And so I will have something like 1 over square root of mass I. And then I divide and multiply by 1 over square root of mass j. So that's just a mathematical trick. So this enters this guy, this enters this guy, this is no longer there, and I find this which multiplies this guy. So let me show you because it seems complicated, but it's easy. So this, I write it as a square root mass, and I keep one here. I bring the other one here, so I have this denominator. And here I multiply and divide by square root of mass j. So the idea, the reason for why people do that is now this object is the friend of this object. They look the same. This is a matrix, and this is a number. So in practice, you have a situation where you have really clearly a no longer something like that, but something like matrix times vector equal omega square times vector. So that's really a eigenvalue problem, okay? So how do people call these things? This is called the dynamical matrix. So dynamical matrix is the matrix of second derivatives of the energy with respect to atomic positions divided by the square root of the masses. These are called the mass-scaled vibrational eigenmodes because there is a mass factor in the middle. And in practice, what one does is to calculate this object in DFT calculations, okay? So you just have total energy, you evaluate these derivatives, and you try to get this matrix. Once you have the matrix, the whole problem is a standard eigenvalue problem. So you go, back to linear algebra from your undergrad courses. There are techniques to solve these problems. So what you want to find basically is the eigenvectors and eigenvalues of these matrices. Okay, as simple as that. So this is a very simple operation compared to DFT calculations in the sense that the number of plane waves in a wave function is of the order of tens of thousands, 50,000, things like that if you did a bit of convergence. So there you have matrix vector operations, with giant objects. So here, for a small system, let's say 10 atoms, you have 30 degrees of freedom. It's going to be 30 by 30. So if you try to diagonalize a matrix 30 by 30 in MATLAB, it's going to take a millisecond, okay? So it's really a simple problem at this point. So the difficulty is to obtain really the total energy and then to evaluate the derivatives. So that is the time-consuming part. Everything else is easy. Okay, so that's basically what people do, and that's pretty much it. So after you have that, you will have eigenmodes, you will have eigenfrequencies, and you discuss basically the normal modes of vibrations of a molecule or a solid. So the question is now, how do people get derivatives of the total energy? So that is not difficult. You can use finite difference formulas. Okay, so if you want to do the derivative of the second derivative, you can take a point here, one here, and you basically do this plus this minus twice that, divided the step square, and that's the second derivative. So there is nothing. So one can do that. And in many cases people do this. Okay? So that's a possibility. So for each, basically what happens, so here I'm showing only the second derivative with respect to the same atom. If you have a second derivative with respect, let's say, to atom 1 and then atom 2, basically you need to move the atom 1 and then do displacement of the second atom, and so on. So this means that for each atom and for each Cartesian direction, you need to displace another atom and another Cartesian direction. So it's a lot of calculations. So in practice, doing this, it's possible, and many people do that. But you end up doing a lot of calculations to move atoms around and look at how the total energy changes. There's a slightly smarter approach, which is the following. So we want essentially second derivatives of the total energy, which is with respect to position. So that is essentially the first derivative of a first derivative, right? Which is a trivial statement, but we know that the first derivative is minus the force. Okay? So that's minus the force on a given atom. So instead of calculating second derivatives, okay, which requires 1, 2, 3 points, if you do the derivative of the force, you only need 2 points. So since the force is something that you've seen yesterday in tutorials, it can be calculated quite easily now. So people prefer to look at the force after you displace an atom, and then you do the calculation of the atom displaced the other way around. You take the difference, and that's basically an approximation for this second derivative. Okay? So all of this is equivalent theoretically. This is way faster because you have to do fewer calculations. So that's is essentially a way of using finite difference formulas for calculating second derivatives of the total energy. Sometimes people call this the frozen phonon method, but that's actually an inappropriate use of language because we are not using, you are not freezing phonons. We are actually just displacing atoms one by one, so there is no phonons yet. Okay? But sometimes in papers you see, oh, I'm using frozen phonon approach, which is basically means using finite differences, although it's not, there is no frozen phonon anywhere, okay? So that's basically one observation. Now this is basically the brute force way of doing calculations of eigenmodes. So there is a much more elegant approach, which is called density functional perturbation theory. So in the same way, you can study the response of a system to an electric field by either, so if you look in, imagine the hydrogen atom, going back to quantum mechanics, 101, you can study the effect on electric field by placing an electric field in the Schrödinger equation, trying to find a solution, or you can use perturbation theory, okay? So use the prescription of perturbation theory to get the same result. So density functional perturbation theory basically tries to determine the second derivatives by evaluating this so the potential energy surface for displaced nuclei in perturbation theory. So it's identical to the standard perturbation theory, but it is called density function perturbation theory because when you move an atom, you're not just looking at the change of the wave functions and the eigenvalues, like in standard perturbation theory, but there's also a change of density. So there is an extra complication. So there is a bit of technology behind that, and that is described in this review paper. So that's basically how people do these calculations. And today in the afternoon we will see the first calculation. We will try, I think, chlorine again, and possibly, and we will try this approach. And then we will look at phonons and eigenfrequencies using this approach, which is clearly faster also. This is essentially corresponds to a number of calculation which scales with the number of atoms that you have. This is one calculation. Okay? So if you have a very large system, this becomes almost impossible, and this is doable. So this is an example calculation that I did for water. Okay, So what you see here is just the dynamical matrix that I calculated for water explicitly, doing second derivatives, brute force, so by hand. So you move atoms and then you get the values. And I did not write anything here because the matrix is symmetric. So the lower triangle is identical to the upper triangle, basically. So I don't write it down. So that's basically how the dynamical matrix of water looks like, the water molecule. And this was done with this calculation that I showed, this box I showed you at the very beginning, where I place a water molecule in a large box. So there's only one water molecule. That means 3 atoms. So 3 atoms means 9 degrees of freedom. So here you have 9 columns and 9 rows, okay? So if you have 9 degrees of freedom, you have a 9 by 9 matrix. So if you diagonalize that now, you can find the eigenmodes and the eigenvalues. What we expect here is the following: 9 eigenvalues, okay? So that's pretty clear. However, out of these eigenvalues, 3 eigenvalues are rigid translation of the molecule. So basically, there is a molecule which could move left, basically x, y, or z. So these are not vibrations. It's just a translation of a rigid translation. So those don't matter. Then there are 2 librations. So the molecule can do something like that or something like that. Okay. So these are not vibrations. Okay. So you can always choose a reference frame where that doesn't happen. And then there is one mode which is spinning. So you can actually have the molecule spinning around. Okay. So that is also not a vibration. So there is only actually 3 modes, which are the internal vibrations of the molecule. Okay. So we need to look for 3 eigenvalues and 3 eigenmodes. So here what I'm giving you is the eigenmodes that I found. So the arrow represents basically the displacement u that you find as eigenvector of this matrix. So a displacement can be represented as an arrow. So here, for this eigenmode, the arrows goes this way. For this eigenmode, it goes this way, and so on. So clearly, this means that this molecule is doing that. So this mode is called the bending. Here they are basically doing that. So this is called the stretching, symmetric stretching. And then in this case, it's still stretching, but they're going opposite ways. So this is called asymmetric stretching. So the reason for the naming is just visual. So people look at it and give these modes some names. Typically, the names are quite fanciful. I mean, it's depending on the imagination of the person who finds them the first. So if you look at the frequencies now, the calculation gives for this bending mode 189. So in the experiment, in this case, it's 198. So it's 5% off. The other 2 are a bit better, but clearly you can tell that the agreement is of the order of 5%. Okay. So this is typical. This kind of agreement is what you usually get in these calculations. Okay. So that's basically to finish, to tell you something about vibrations in very simple systems. And again, we have basically harmonic approximation, second derivative of total energy, and looking at the, diagonalizing a matrix. There is nothing more than that, okay? The situation becomes, so this is basically the second level of complexity. We have a diatomic molecule, 1 degree of freedom, easy, everything is scalar. In the case of polyatomic systems, you have matrix problems. The next level up in complexity is infinite solids. So when you have a crystalline solids where the unit cell is repeated everywhere, okay? That brings just a little bit of complexity. So I'll try to do it, and this is a bit boring, but I've been asked to explain what phonons are. I guess that's, you have to go through it. There is only just basically one extra piece of information which we're going to discuss now, is the fact that the solid is completely translationally invariant. Okay, so that piece of information brings a qualitative new feature in the calculations. So the easiest way I have to explain that is to consider again a system with very, very few degrees of freedom. So here what I'm considering is a chain of atoms. Okay, so this is atom, atom, atom. They can only move along the x direction, so along the direction of the chain. So for each atom there is only 1 degree of freedom. Okay, all the atoms are identical, so we don't need to worry about the masses. And that's it. So that's basically the simplest possible system you can imagine if you are looking at an extended solid. So in this representation, what you see basically is that I get the same chain of atoms, but I displace this one by a certain amount, which I call u. This one a bit larger, this one a bit larger, and then it goes back. So this is basically like a little wave going through. And this is basically the counterpart of what we discussed for the molecule. There's a chain of atoms, and each of them carries a displacement. In this case, the subscript identifies the atom. Okay, and let's say if there's one atom per unit cell, it's either the atom or the unit cell. It's equivalent. Okay, and the same for the displacements. So in this case, the story is identical to what we did before. So it's mass of the atom, which is the same for all of them, times the second derivative of the displacement is equal minus this matrix, which is basically the sum of the force constant. So the matrix of the force constant times the displacement. So that's basically the Hooke's law. Okay. So it's basically the law of the spring, but with many springs connected between each other. So that's the counterpart of what we've seen for the water molecule. The only difference is that I dropped all the Cartesian directions because we only have one direction, and I'm asking the system to have all the masses to equal masses, so it's a bit easier. So basically, this is the problem. Okay. So why this is slightly different from what people discuss in the case of molecules is basically because this equation, even if you cannot tell probably by looking at that, is actually almost identical to the wave equation. So we have a second derivative here and a second derivative here. Actually, you may not see that, but if you do the maths, you will recognize a bit of an analogy. But most importantly, if you think about vibrations in a solid, are part of that gives rise to sound. Okay, so the transmission of sound through a solid goes via vibrations. So that means that pressure waves in a solid, they must kind of satisfy this kind of equation. Since pressure waves are related to vibrations, it must be that also this equation has to have solutions which look like the solutions of the sound wave equations. Okay. So what are the solutions of that? It's easy to check that if you replace just a plane wave like that. Okay. So some amplitude and exponential I qx minus omega t. So it's just a propagating wave. If you replace that here, you find basically the dispersion relations for sound. So there is nothing really complicated. So the idea is that if those two are friends, and if this is the solution to the sound wave equation, it must be maybe possible to write down solutions of this in the same form. So that's the idea. So now I'm making it very complicated. It seems something exoteric. But if you go to Kittel, page 3, it tells you, oh, the solution is going to be like that. That's it. So I mean, I'm just trying to make it, to expand a bit more on that. But in principle, we are supposed to understand that that is the case anyway. So when you do that, basically, you say, OK, I would like to find a solution which looks like that. What I can do is to look for a solution with an amplitude. A complex exponential will have q times x will be the position. In this case, will be the position of the atom, minus omega t, which is the frequency and the time. OK? So that's basically an ansatz. We are asking, if I replace that inside this object, do I get anywhere? Okay? So people try that, and let's see what happens. So I'm going to do a couple of steps. I know that's boring, but at least we can all follow. So if I replace that inside this, again, the omega comes down, because we have second derivative. It's going to be omega squared. And that's pretty much it. We will have exponential IQ Ri on this side, and exponential IQ Rj on this side. So this is it. So what I can do is now to bring the mass on the other side, divide everything by that. So I find this expression. So that gives me an expression for the frequency in terms of the mass, the force constant, and these prefactors. Okay. So far it's just some simple maths. So now the most important observation is that this is the derivative of the energy with respect to an atom, second derivative with respect to atom I and then atom J. Okay. If the solid is a translationally invariant, if I move everything by, let's say, 10 unit cells, this number cannot change. Okay, so this number has to be the same everywhere. So that's basically the translational invariance of the force constant. So if I shift by any number of unit cells, nothing changes. Because of that, what I can do is to rewrite this as, maybe I can show it. So instead of Kij, I can rewrite it as Ki minus J, J minus J. So I translate everything by J. Okay? And at this point, what happens? This becomes 0. And this becomes my dummy variable. Okay? So the bottom line is that this expression simplifies, and I basically have sum over j, something which depends only on j, and then this exponential factor. If you look at this expression, that is a Fourier transform. Okay? So in the case of solids, what happens is that the frequency now will carry a dependence on this kind of wave vector here, which is the phonon wave vector in practice. So what happens is that now the frequency will depend on the wave vector, and this wave vector, is what determines, is essentially the one which decides the Fourier component of the force constants that you're looking at. So that's why we have phonon dispersion relations, essentially. Okay, so the Q vector is just the wave vector of the wave that we are using as a possible solution. So that's the easy bit. So we did this now, and it's all trivial. So this is the kind of maths we are doing, so it's very, very simple. And that's just to remember what's going on. So in practice, the situation for a three-dimensional solid is a bit more messy. So that's actually how a dynamical matrix looks like and how a DFT code calculates it. Okay. So instead of having ij, we have I and then Cartesian coordinates, j and the Cartesian coordinates, because we are in 3D. Then here there is 1 over mass. That becomes 1 over square root of the mass of the first and mass of the second atom. Okay. Then we had exponential IQR. This was one-dimensional. In 3D, you get scalar products. Q, it becomes a vector. The position is a vector. And then typically what people do is to use capital R to indicate the unit cell, and then lowercase tau to indicate the position of the atom in each unit cell. Okay. So that's a standard expression. So what you can see basically is that this is the concept. Okay. So from this step to this step, there is nothing new. We're just adding atoms and different masses and Cartesian coordinates. Okay. So that can also be derived exactly the same way I did, but it would take us an hour to do that properly. But basically, if you remember that, if you have a vague idea about that, at least you can remember how people, why people obtain some kind of wave vector in the phonon dispersions. Okay. So at this point, this is again a dynamical matrix, and we find the eigenmodes and the eigenvectors by diagonalizing the dynamical matrix. Okay. So since the dynamical matrix depends now on the wave vector, what we do is to diagonalize this matrix for each wave vector. Okay. So you have vibrational modes and vibrational frequencies at each wave vector. So that's an example calculation for diamond. Okay. So I'm putting this here because there are very, very nice experiments which were done, I think, in the I don't know if in the 50s or the 70s. So basically, the black lines is a DFT calculation, and the blue dots are inelastic neutron scattering. So the story of this actually is quite interesting because so these measurements actually were really done on this sample, which is called the Oppenheimer diamond. So if you go to the Smithsonian, you see that. It's something like that. So it's the largest diamond existing on this planet. So to do this measurement, basically imagine transporting this diamond to Los Alamos and doing the measurement on neutrons. So they had a special permission or something to do that. So it's quite interesting. So basically, this is just to say that if you try to do calculations, you get quite close to experiment. You see, it's almost impressive, the agreement. And at this point, on this axis, we have the wave vector. Okay. So these lines are going through the Brillouin zone. I guess it's going from gamma to x, means that from the center of the Brillouin zone, it's going here. Then from x, from x to gamma along delta is the other direction, this one. And then this gamma to L is the one which goes towards the hexagonal phase. So in principle, you would like to show dispersions throughout the volume of the Brillouin zone, but it would take forever. So people slice a little bit, take some special directions, and show how these things change along these special directions. Typically, special directions are quite representative, so you don't need to do everything. You just do a few which are people agree that they are important. So the way to see this plot is the following. If you choose a wave vector, okay, so that gives you one dynamical matrix from the calculation. In the case of diamond, we have 2 atoms per unit cell, so 6 degrees of freedom. So you expect 6 eigenvalues for each wave vector. So you would have 2, 3, 4, 5, and 6. So here, 2 are degenerate and 2 are degenerate. Okay, so that's the way it goes. So you will have 6 throughout at each wave vector. So that's when you see phonon dispersion relations in papers, that's basically what it is about. I mean, it's not really complicated. It is just a dynamical matrix carries a dependence on the wave vector. Okay? And I just want to show one last example. If you have, in crystalline solids, you have things like phonon dispersion relations. Sometimes you have situations where you don't have a crystal, you have an amorphous solid. It is still meaningful to calculate phonons and vibrations. In that case, you don't have dispersions like that, but you can count how many states, vibrational states you have per energy interval. That's called the vibrational density of states, okay, that you see in many papers, obviously. So I'm showing an example of a calculation on vitreous silica. So this is a model of amorphous silicon dioxide. Basically, this is the vibrational density of state, so how many phonons you find per unit of energy, okay? The black line is the DFT calculation, and the blue dots, the blue circles are the inelastic neutron scattering data. So this is also very good agreement, but clearly you see there are some discrepancies. So that's an interesting bit, an interesting point, because one could say, oh, is the discrepancy a problem of DFT or not? Well, here there are basically two problems in this calculation. One is that this is a model of an amorphous solid, so nobody gives us the coordinates on amorphous solid. This has been determined by many calculations and many studies where essentially by making sure that all the short range and the medium range structures, they agree with various experimental probes. So that's one of the best models we have now. But there is no guarantee that this is perfect. So we're not comparing a crystal with a crystal. So this structure, basically, what I'm trying to say is the blue circles correspond to a structure which we don't know yet. So we just hope that this is a good model. The second thing is that in the neutron scattering data, there are various, basically other complications, like the cross section for the neutron scattering is there and changes the heights of the peaks. And in this calculation, I did not correct for that. Essentially, this is just a phonon density of states. I'm not taking into account the scattering cross sections. Okay, so clearly the heights of the peaks are not going to be identical. But you can see that we are quite close. I mean, which is quite impressive. So I think this is basically the end of this lecture. So in the next lecture, what we're going to try to do is something, one step up from this morning, which is basically a calculation of dielectric constants and IR spectra using basically what we learned about phonons. Okay, I guess.